The Milky Way galaxy has a diameter of 100,000 light-years and contains 1 trillion celestial objects. Where within this vast galaxy is our solar system located? Let us go there. At this speed, we would pass the Sun in an instant, so we will gradually slow down. The solar system is coming into view. As you can see, we understand the position of the solar system with considerable accuracy. Why, then, are we able to determine the position of the solar system within the enormous Milky Way galaxy? When we want to know our current location, we tend to imagine it from a bird's-eye view. For this reason, to indicate a specific location, we need information about the surrounding area. In other words, a map. The same is true for the solar system. To know where it is located, we need a map of the Milky Way galaxy. The more accurate the map, the more precise the determination of the solar system's position will be. Humanity has long engaged in mapping the universe and the Milky Way in order to find the solar system's position. Let us go back more than 200 years to around 1800. William Herschel, an astronomer and composer, thought of creating a map of the Milky Way by measuring the distances to stars. He used the brightness of stars for this purpose. Light follows an important principle. It diminishes in intensity with the square of the distance. For example, if the distance from the light source is doubled, its brightness becomes 1/4. If tripled, the brightness becomes 1/9. Therefore, if one can accurately measure both the intrinsic brightness of a light source and its apparent brightness from a certain observation point, one can determine the distance to that source precisely. William Herschel applied this principle. He first assumed that all the stars in the universe have the same intrinsic brightness. Thus, differences in apparent brightness would be determined solely by their distance from Earth. For instance, the Sun is the brightest star because it is closest to Earth, and other stars appear dimmer because they are farther away. He selected relatively bright stars in the night sky, measured the brightness of each, and plotted their distribution. This is the distribution map Herschel created. It shows stars distributed in a disk shape with the Sun at the center. However, this is entirely different from the galaxy as we know it today. Herschel himself realized the flaw in his map. His assumption that all stars have the same intrinsic brightness was incorrect. It is impossible to know the true intrinsic brightness of each star, so measuring distance based solely on brightness is inherently inaccurate. Although Herschel's galactic map was inaccurate, his pioneering effort to depict the shape of the galaxy remains celebrated today. In the latter half of the 1800s, a new method emerged for measuring stellar distances: measuring angles. This method uses a right triangle. A right triangle is a special geometric figure in which, if the height and one angle are known, the lengths of the other two sides can be calculated. Thus, if we can draw the base of a right triangle between Earth and a star, and know the height and an angle, we can calculate the base length, which represents the distance to the star. How is this right triangle drawn? Earth takes 1 year to orbit the Sun. 6 months later, Earth's position is on the opposite side of its orbit from where it is now. This orbital diameter serves as the triangle's height, with the base and hypotenuse extending toward the target star. However, the angles involved are extremely small and difficult to measure accurately. To improve precision, astronomers use a reference star. When Earth moves in its orbit, the target star appears to shift relative to this reference star. This apparent shift enables the drawing of the right triangle and allows for more accurate angle measurement. This apparent angular shift caused by Earth's orbit is called stellar parallax, or annual parallax. Once the parallax method was established, astronomers around the world began competing to measure stellar distances. The winner of this race was the German astronomer Friedrich Wilhelm Bessel. He measured the parallax of 61 Cygni as 0.314 arcseconds. From this value, he calculated the star's distance to be about 10 light years, almost identical to the modern measurement. Thus, by using right triangles, one can accurately determine the distances to stars. However, parallax has a drawback. The farther the star, the greater the measurement error. Nearby stars appear to shift position significantly when viewed from slightly different locations on Earth's orbit. Distant stars, however, shift so little that the measured angle approaches zero. For example, here are two photographs of the same region of space, one taken from Earth and the other from near Pluto. The star that appears to move is Proxima Centauri, the nearest star to the Sun. These images were taken by the New Horizons spacecraft as it traveled toward Pluto. The distance between Earth and Pluto is about 30 to 50 astronomical units. This is the largest parallax baseline ever used in human history. By comparison, the baseline from Earth's annual orbit is only 2 astronomical units. Even with a baseline more than 15 times longer, and even for the nearest star to the Sun, the apparent movement is minimal. The farther a star is, the smaller the apparent movement, meaning that even tiny angular errors result in large distance errors. With the technology of that time, measuring parallax beyond about 100 light years was impossible. Thus, another method was needed to map the galaxy. In the 1900s, a new approach was added, using Cepheid variable stars. A Cepheid variable is a star whose brightness regularly increases and decreases over a fixed period. American astronomer Henrietta Swan Leavitt studied Cepheid variables in the Magellanic Clouds. The distance to the small Magellanic Cloud is about 200,000 light-years. Since the stars in it are roughly the same distance from Earth, differences in apparent brightness caused by distance can be ignored. Leavitt examined thousands of Cepheid variables within the small Magellanic Cloud, and precisely measured their brightness variation periods. The changes were remarkably regular. When she plotted luminosity on the vertical axis and period on the horizontal axis, she found a precise correlation. Therefore, by measuring a Cepheid variable's period, one can determine its intrinsic brightness, and from that, its distance. This breakthrough allowed astronomers to measure distances to Cepheid variables and produce much more accurate maps of the Milky Way. In 2013, humanity launched a satellite to create an even more precise galactic map. Gaia. Gaia carries 3 main instruments. First, the astrometric instrument ASTRO, which can measure the positions of celestial objects fainter than magnitude 20 with extreme precision. As explained earlier, knowing an object's angular shift allows calculation of its distance. ASTRO's accuracy is so high that for objects brighter than magnitude 15, the error is only 26.6 micro-arcseconds, making it possible to measure distances to stars far beyond previous limits. Second, the photometer, which measures the intensity of electromagnetic waves from 320 to 1000 nanometers. That is visible light plus adjacent ultraviolet and infrared. It disperses the light into a spectrum, much like a prism producing a rainbow. Dark lines in this rainbow can be analyzed to determine a star's temperature, pressure, and chemical composition. Third, the spectrometer, which also disperses light but focuses specifically on the dark lines caused by ionized calcium. By measuring shifts in these lines, Gaia can determine a celestial object's rotation, direction of motion, and speed. Using these three instruments, Gaia can reveal the positions, motions, and types of astronomical objects. On December 19, 2013, a rocket carrying Gaia was launched. After about 3 weeks, Gaia reached the Lagrange point L2, about 1.5 million kilometers from Earth. Since then, it has observed over 1 billion celestial objects, including stars, planets, comets, asteroids, and even distant quasars, delivering all this data to us. From these observations, it is producing an extremely accurate three-dimensional map of the Milky Way galaxy. Long ago for humanity, Earth was the entirety of the world. To understand its true nature, our ancestors crossed seas and explored unknown continents. Today, we can observe Earth accurately and objectively. Like the people of the past, we have a curiosity about the universe and a desire to understand it completely. With Gaia continuing to deliver its ultra-precise cosmic maps, one day we may wish to travel the universe, map in hand.